All right, so this is 127, and let me bring up the schedule. All right, so here we are. We're going to do the first part of Windows Overflows here, and next week Caitlin will be a guest lecturer. She got the exploit development certification, and she can tell us about that, and then we'll have more about Windows. Okay, so that's the future, and let's start with some stuff about Windows. All right. So we'll talk about the thread and process environment block, buffer overflows, ASLR, exception handlers, structured exception handler protections, and some more defenses. So the thread environment block has information about the currently executing thread, and it's partially documented, but a lot of people have figured it out. So this is a fairly common thing at Microsoft. There is an API, an application programming interface we've talked about, that they want you to use and they document. And then there are private functions they don't want you to use. They're for Microsoft internal use only, I suppose. But people just figure them out and put them on blogs, and then they become effectively public, and that's what's happened to a lot of this. So the thread environment block will tell you things like where the import address table is and what the last error is, and so on. And it looks sort of like this. You can see it on Wikipedia. So here's the structured exception handling frame, the stack base, the stack limit, and there's many more things here. So it's sort of like the memory map of the program, giving you the memory location of important parts of a running thread. Now, you've probably seen these when looking in Ollie Debug or other debuggers, the segment registers, FS and GS. These go all the way back. In the old days, you'd have a register to keep track of memory segments, and now FS is used to point to the thread environment block. Now, the process environment block is even more opaque and only supposed to be handled by calling subroutines in internal fields. There's a few fields documented, and here some of them are, whether it's being debugged, and the base address of kernel 32 and ntdil, and something about parameters and the session ID. So these are pretty dense, detailed things that you might use when developing complicated exploits, but we're not going to work directly with these components in this class. All right, so then we have the classic stuff, the stack-based buffer overflow, which is what you've already been exploiting in the Windows projects you've done so far. So this is the classic technique, just like we did in the Linux project ED202. So you overflow a variable, a string variable on a stack, and you overflow the return address. And when that function returns, it now puts the injected return address into the instruction pointer, and now you point that to an attack. So it looks like this. You have something like a name variable. It's only supposed to hold 20 characters, but you overwrite it with a lot more than 20 characters, and you put in a bunch of nops and then an egg, like a Metasploit payload or some kind of shellcode, and then you put in enough padding to reach the instruction pointer. Then when this routine returns, it goes to your chosen instruction pointer value, and you make it point back to somewhere on your NOP sled, and then it goes nop, 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 egg, and you get to win the box. This is the classic buffer overflow, where you inject executable code on the stack that is intended to be a string, and then you jump into it and execute that code. And this was the basis of a huge family of malware right up through Windows XP. And with Windows Vista, Microsoft started putting in strong defenses to prevent this stuff. So this is the game. You overwrite the structured exception handler that points back to the stack. That's one way to do it. Well, this is where you overwrite EIP. Now you can also do this with the exception handler. If you are able to overflow and hit the structured exception handler, which is what we're going to do in tonight's demonstration, then you haven't directly controlled the EIP, but you controlled the handler. Then you have to trigger an exception by doing something illegal, like divide by 0. Then it will go to run the exception handler, and you have modified the address of the exception handler, so now you get an address you can control, and you point that to your injected code. So that's here. You flood this, and you hit the exception registration address, and you put a pointer there that goes back to your NOP and egg. So it's similar to the previous one. All right, so Address-based layout randomization means every time you restart a process, it will randomly relocate in memory, and that makes this difficult because even if you gain control of an address, you don't know what address to put in there because you don't know where your code is. So that's annoying. Without address-based layout randomization, it will just use the first area of memory for this, Windows then for antivirus, IIS, SQL Server. With ASLR, it will just all be randomly placed in memory, and therefore you won't know what address to jump to. So what we did last time was we found that ESP pointed to the stack, and all you had to do is jump ESP. I think we might have done a pop return, another similar one. So this is where you use trampoline. You find code that is not randomized, and you find a couple of machine language instructions you like there, and you jump to that location and bounce off of those instructions back to where you want to be, like ESP. So I don't know where I am, but I do know that ESP points up here to NOP. So I just have to find a jump ESP somewhere and bounce off of that. That's trampoline, the simplest form of a return-oriented programming attack. It used to be that the structured exception handler address was just in EBX, so you could just write to EBX and you'd be writing to the exception handler. But nowadays that's blocked. However, you can still find the SEH address at ESP +8, so pop return is handy, and that will get you into the structured exception handler, and then you trigger an exception. So these are ways to get to code that you've injected even though you don't know where it is. You find a way to find some instructions you can find, which will bounce you back into your code. By the way, there's a simpler technique called the heap spray, which is even more nasty. Since you don't know where you are, you just repeat your exploit hundreds of times, jumping at random until you happen to hit it. And you make a really big NOP sled, so you don't have to get too close. That's another way to go. All right, so the exception handler is here, and the point of this is when something bad happens and the code cannot continue to execute in sequence because an exception has occurred, it goes to your exception handler, and this is where you can say, if a bad thing happens, do this. If a different bad thing happens, do that. So you'll have a series of routines, each of which check for certain error conditions, is the idea, and then return to it. So that's the exception registration structure, and so it has a series of these, pointer to the next structure, pointer to the exception handler. So here you go to the next record. Here's the pointer to go run some code to see if you want to do something about this exception. If that does not resolve it, then you go to the next one and try that, the next one and try that, and that's the structured exception handler, trying all these techniques. And if none of the code written by the developer handles the exception, then it goes to the operating system, which will then pop up some Windows default box, like your program has stopped. Do you want to restart it, or something like that? So here's an example code. You're in the exception handler. Here would cause an exception. So here I fill EAX. You can do this, by the way, in C. You can put assembly code in your C code with this ASM flag. And so I XOR EAX with EAX, which will put 0 in it, and then I jump to address 0, which is not valid. So this is one form of exception. And when you do that, it will then go to the exception handler. And up here I've defined an exception handler. This one just prints a message and stops, but a real one would presumably read some variables and then print out an informative error message to the user and stop, or give the user some other option besides stopping, depending on how you're going to handle the exception. So you can see it in Immunity. You just open the exception handler. It's in just another structure you can see in the debugger, and you'll just see this one is just using Microsoft's default handlers, ntdil, ntdil, ntdil. So the notepad itself didn't write an exception handler. It's just going to Windows operating system exception code. And all right. And so if you follow the address, you'll see the pointer to the next SEH record here, and on you go. Here's the end of the SEH chain. So you can view it if you like. If you go back here, you see this is D9FECC, and you can view that code here and see there's the SE handler, and here's the pointer to the next record, here's another SE handler, and so on. All right, so if you overflow the stack, hit the return address, then you will perform collateral damage. And if you remember in ED202 and the earlier projects, I mentioned that these quite a few of these, you get them to do something fun and then it crashes because we didn't really fix the collateral damage like fixing the base pointer. So you might cause exceptions in addition to your overflowing the return address if you're not careful to undo the damage caused by your overflow. All right. So on earlier, you used to be able to use EBX to find the exception registration structure, but no modern supported version of Windows does that anymore. That was one attempt to try to make these exploiting more difficult. And so in the old Windows process, when things crash, EBX will point to the structure, so you can overwrite it. You know with EBX is where you go to gain control of the instruction pointer. On modern processes, when the stack crashes, the third value down here points to the exception registration structure. So you can still find it. And as you see here, I was able to overflow it, so we gain control of this. And so I'll have a demonstration later where we'll do that. All right, so Microsoft has been adding more protections. In Windows 2003 Server, they added some more attempts to make sure that a handler is a valid handler. So if it's on the stack, you're not allowed to execute that code. It won't let you do it. If it's in a loaded exe or DIL, it might go for it. There's modules that are marked not allowed, so you can't have the exception handler in there, so you're not allowed to go point to those code, and so on. There are some attempts to stop you from exploiting it here. And that's another spam call. All right. So you can abuse an existing handler, find code in an address outside all modules if you can find it, or use code in some module that doesn't have those defenses. Those are one way to get around it. And then there's later defenses that came out with Vista and Server 2008. And so here's a normal SEH attack. You have a series of handlers here, and then you go to the end. And when you overwrite it, you're going to change one of these codes. It's going to go to a pop-pop return. So the exception handler chain is no longer going to hop through various things and hit this flag value at the end. So Safe SEH is a compiler switch. You can, if you write your code with Microsoft Visual Studio and you compile it with this switch, it will then create a whitelist of exception handler addresses. And so it will not let you change any of these addresses to a value that is not what was intended at the time the code was compiled. So you won't be able to add some other address here that points to pop-pop return. This is a very strong defense. The problem is, if you have code that was compiled without this switch, you cannot fix it without recompiling the code from the source code. So programs you purchase and download would have to be updated to new versions to implement this security. SE-hop is another defense. This verifies that the handler is intact before using it. So it's going to go here and notice that this chain was supposed to go through a series of things and then to a flag value, and after it's been broken, it just goes one place and the next thing is not there. So it will notice that you've been overflowing things and contaminating the SEH. All right. And so that you'd have to be much more careful at how you overflow and damage and reconstruct the SEH to prevent SE-hop from stopping you. So it adds an extra record at the end of the list. It walks through the list to make sure that record can be reached. This, by the way, is the same way Cisco routers prevent this. Cisco routers have a heap, and they prevent heap overflows by having a process called check heaps that hops through all the chunks on the heap and make sure it can make it all the way to the end, then hop all the way back to make sure all the next and previous pointers are intact. And if they aren't, that means there's been a heap overflow, and Cisco routers just restart and throw away everything to stop that. So you can't exploit them successfully with heap overflows, and this is a similar defense in Windows. So that's SE-hop. Here's a valid SEH chain. You can get to the end and back, and here's an invalid chain where it doesn't really have a whole chain of useful records anymore. It's turned on in modern versions of Windows by default in the server versions, although not in the client versions like Windows 7 and Windows 10. This is very common. Microsoft Server operating systems are more secure by default because they do not intend them to be all-purpose, so you're not expected to be downloading a lot of random, sloppily written programs and running it on your server. You're expected to get modern versions of things that you can trust that you run on your server, but your client machine, like Windows 10, you probably do want to just download anything and run old programs and stuff, so they make it have fewer of these defenses, so you can run legacy code, which you're more likely to want to do on Windows 10. Even though it's less safe, you're only risking your own machine, not a whole server. All right, and you can control whether this is enabled or not here in the registry. There's a, you can choose a program and you can turn on image file execution options. And here you can disable exception chain validation. So you can turn it on or off, but by default, this protection will be on for servers and off for clients. All right, and if you do have that defense on and you try to do one of these SEH exploits, then you'll get this error in immunity. The debug program was unable to process the exception. You cause an exception and it goes to the exception handler, but then it detects that the exception handler has been modified and it stops with this message. It will not attempt to run the modified exception handler. So it amounts to very much analogous to stack cookies protecting you from buffer overflows. All right, so let's take a look at the Cahoots, which I've got here. This is 8A. And I'm going to get my virtual machines going. All right. Well, that might be it. I'll give it a few more seconds. All right. Okay, switch defense is enabled in servers, but not in clients. Yep, that's SE hop. Also, one thing I found out which horrified me, Microsoft does not include as many drivers in the server version of the operating system. If you have old crappy hardware, servers will fail to run, even though a client version of Windows might run, for the same reason. They only include like the modern and more trustworthy software in the server operating system. All right, what defense cannot protect legacy code? That's safe SEH, a nice strong defense. It won't let you jump to the wrong address, but you have to recompile your code with that switch. All right, what defense can be enabled individually for each process? In Windows 7, and also Windows 10 for that matter, it's SE hop. You can control it. All right. That's the one that applies to the operating system regardless of when the code was compiled. All right, so what's the old exploit method that only works on old versions of Windows? Yep, that was EBX. EBX containing a pointer to the exception handler. How do you defeat ASLR? We did this last time. Pop, pop, return is a trampoline. You find this code somewhere that is not randomized, and you can bounce off that and go to code on your stack. All right, and where's the register pointing to the thread environment block? All right, that's the FS register. All right, I think that's probably Judy. I know who that is. All right, I know who that is. All right. So let me get to